Hi, my name is Ali Ghitani and I will be solving some topic 5 paper 2 questions. Now the first question actually comes from a huge question from the 2017 May exam, and the question combines equilibrium redox processes as well as thermochemistry and energetics. But I'm only going to be concerned with F because it is the only one which covers topic 5. So we're given here our reactants and our products. And the question states to determine the enthalpy change of reaction, or the delta H, when 1 mole of gaseous hydrazine decomposes. Now the composition here, we must identify that it's an exothermic reaction, decomposes to its elements. And here are the elements. Use bond enthalpy values in section 11 of the data booklet, which hints that we're going to be using the periodic table, and it gives us section 11, which deals with bond enthalpies and average bond enthalpies for single bonds and multiple bonds. So now we simply need to know if it's going to be products minus reactants or reactants minus products. So first we need to know which bonds are being broken and which bonds are being formed. Well, products are being broken. So that's our bonds broken. And the reactants are our bonds that are formed. And delta H here is equal to bonds broken minus bonds formed, which means that to get our delta H, we're going to need the values. We're going to get it for each one, and it's going to be reactants minus products. So let's get the values of our reactants first. Well, we have N2H4. Now, our N2 here is simple. It is 158, since it's N with N. So that is a simple bond, or a single bond. Then we have H4 here. When H reacts with H, it has a value of 391. But we're actually going to multiply that by 4 because it's H4, not H2. So multiplying that by 4, we get 391 times 4. We get 1564. Adding our N2, which is 158, we get 1722. So now we've got half of our equation. Our reactants here, delta H, is equal to 1722 minus. Now let's take a look at our products. Well, our products here are actually tricky because we have N2. So we might just simply go to the single bonds and look at N and its value with N, which we did with the reactants. But actually that's not the case, because N has 5 valence electrons, so it actually has multiple bonds. It's a triple bond. So you don't say, or actually it's not even, yes, it is a triple bond. So we don't say that N and N, it's simply as it says here, the single bond's 158. We have to look at our multiple bond values, and we see that N triple bond N, so N triple bond N is 945. So that's something that's very important here. It's where most people lose marks. So now what's left is our 2H2. It's simple. We get the H2 from the simple bonds, which is 436, and then we multiply that by 2 because of our coefficient here beside the H2, which is 2. And when we add and simplify both of those, we get that this is equal 1817. So our bonds here are 1722, and our bonds here are 1817. plug that in with the delta H, we get a delta H of bonds broken minus bonds formed of negative 95 kilojoules, which proves that this is exothermic, which has a negative value since we said here that it decomposes. Now this question is from the May 2018 paper 2 as well, and for this one we're not gonna only use section 11 from the data booklet, but also section 12. So we are told that under certain conditions, ethane, which is 3 carbon 2 hydrogen 2, can be converted to benzene. And then we're asked to determine the standard enthalpy change, delta H, for the reaction using section 11 of the data booklet. So far so simple. We already know from our last question that it's bonds broken minus bonds formed. So let's get our values straight. We know that it's gonna be reactants minus products since it's bonds broken minus bonds formed. So the first thing here we have is 3 here for the carbon and the carbon bond, which is gonna be 839 if we look at the multiple bonds section from section 11. And then minus 6 for the carbon bond times 507. So let's get our values straight. The 839 times 3 relates back to our ethine, and then the 6 here times 507 relates back to our benzene. And those values could be found in the data booklet section 11 part. So now this 3 times 839 is going to be 2517 minus 6 times 507, which is 3042, gives us a delta H of negative 525 kilojoules, which means that this is an exothermic equation. For question number II, we have a different situation because we are asked to still determine the standard enthalpy change of delta H for the following similar reaction using delta HF values in section 12. F of course stands for formation of section 12 of the data booklet, not section 11. Now section 12 deals with thermodynamic data and selected compounds. So here the substance itself has its delta H and F, and there are other values there, but we're only going to use our delta HF. So here at the beginning it used to be reactants minus products. Here our delta H of F is gonna be products minus delta HF of our reactants. Now our reactants are still ethine and our products are still benzene. So let's look at our product here, which is C6H6. Looking at section 12, we have a positive value of plus 49. And our reactants are C2H2. Looking at C2H2 ethine, we have a positive value of 228. One thing that's important to note here is that we have to multiply by 3 because our ethine has a coefficient of 3 at the beginning. So this is going to be multiplied by 3. So simply simplifying this as our product, 49 minus 228 times 3, we get a negative delta H of 635 kilojoules, of course.